Hello, this is Bono. Today I'd like to talk about the theme of Ohm's law. In the section so far, we've learned the three words voltage, current, and resistance, each on their own. Voltage is the push that drives the current is the amount of electricity flowing, and resistance is how hard it is for electricity to flow. In fact, these three are not separate things, they tie together neatly in a single equation. That equation is today's lead, Ohm's law. Once you understand this law, you can, for example, work out on the spot, if I connect this resistor to this source, how much current will flow. You'll be able to handle circuits with numbers, not just a vague feel. The first step toward that is this Ohm's law. By the time you finish this video, you'll be able to explain in your own words what relationship Ohm's law expresses and how to use it to calculate the current or the resistance you need. The only math involved is multiplication and division. There's no difficult math, so please feel free to watch to the end. So let's get straight into Ohm's law itself. For one resistor, Ohm's law says this: the voltage across the resistor is proportional to the current flowing through it, and the thing that sets the degree of that proportion is the resistance. Here, let's write voltage as V, current as I, and resistance as R. Then this relationship can be written as voltage equals current times resistance, that is V equals I times R, or in short, V equals IR. This is the most basic equation in electric circuits. Let's think about what proportional means using a waterway. Voltage is the push on the water, current is the amount of water flowing, and resistance is how hard it is to flow. Keeping the difficulty, that is the resistance, the same. If you double the push, the amount of water flowing also doubles. Double the voltage and the current doubles too. That is what proportional means. Now this time keeping the push, that is the voltage, the same. What happens if you only double the difficulty? The path is twice as hard to flow through. So the amount of water that can get through is halved. For the same voltage, double the resistance and the current is halved. The larger the resistance, the smaller the current. This is an easy place to mix up, so keep in mind, the larger the resistance, the smaller the current actually gets. To sum up, voltage and current are proportional, and the proportionality constant is the resistance. As an equation, V equals IR. This single equation is the starting point for everything today. This equation becomes very easy to remember using the triangle figure we'll show next. Ohm's law is used by reshaping it into three forms to fit what you want to know. But if you try to rote memorize the three equations separately, you tend to get tangled up over whether it's division or multiplication. That's where the handy VIR triangle comes in. It's very simple to use. First, draw one triangle, write V in the top, and in the bottom write I on the left and R on the right, then just hide the letter you want with a finger. The arrangement of the remaining two letters becomes the equation you're after. Let's go through them in order. When you want the voltage V, hide the top V with your finger. Then in the bottom row, I and R remain side by side. Side by side means multiply. So V equals I times R. Next, when you want the current I, this time hide the I at the bottom left. Then V on top and R at the bottom remain. Stacked top and bottom. A top and bottom arrangement means divide top over bottom. So I equals V over R. Last, when you want the resistance R, hide the R at the bottom right, and V on top and I at the bottom remain. This is also top and bottom, so R equals V over I. Like this, all you have to remember is one thing: the arrangement of the letters in the triangle. After that, just hide one and you can build the equation you need on the spot. There's no need to rote memorize the three equations. So from here, let's use this shape to actually do some calculations. So next, let's actually use this equation. First, the pattern of finding the current that flows. Ohm's law was the single equation V equals IR. We reshape it to fit the quantity we want. Right now we want the current I. So dividing both sides by the resistance R gives current equals voltage over resistance, I equals V over R. This is exactly the same as the original equation, just resolved for the current. Let's actually do it. Say you connect one 5 ohm resistor to a 10 volt source. The current that flows is voltage over resistance, so 10 volts over 5 ohms is 2 amperes. So we've calculated that 2 amperes flow in this circuit. Like this. If you know the source voltage and the size of the resistor you connected, one division gives you the current. Even without connecting an ammeter to the circuit, you know the current in advance. This is what's handy about Ohm's law. Next is the reverse pattern. This time let's find the resistance you need. In actual circuit building, it's common for the current you want to be decided first, as in I want about this much current through this part. In that case, you solve Ohm's law for the resistance. Dividing both sides of V equals IR by the current I gives resistance equals voltage over current, R equals V over I. This too is a rephrasing of the same equation. Let's look at an example. Say you use a 10 volt source and want 20 milliamperes to flow. 20 milliamperes is 0.02 amperes. The resistance you need is voltage over current. So 10 volts over 0.02 amperes is 500 ohms. In other words, if you put in a 500 ohm resistor, exactly 20 milliamperes will flow. To find the current, it's I equals V over R, and to find the resistance, it's R equals V over I. It may look hard, but it all comes from the single equation V equals IR. Just think of it as reshaping the equation to fit what you want to know and you'll be fine. Here's one important caveat. It's about the premise for Ohm's law to hold. So far we've said that voltage and current are neatly proportional. But this always holds only when the resistance R is constant. To put it a bit more carefully, it means when conditions such as temperature don't change and the part's difficulty to flow stays at the same value throughout. The resistors we usually use are exactly the leading example of R is constant, and Ohm's law holds cleanly and comfortably for them. That's why we could do those calculations earlier. On the other hand, there are also parts in the world whose R is not constant. For those parts, voltage and current don't stay neatly proportional. This is actually an important checkpoint when using Ohm's law. In the next field fact, let's look at the leading examples. Here's a field fact. The theme is parts where Ohm's law doesn't work. Ohm's law is a basic of electricity, but in fact it is not an all-powerful law that holds for every part. There are parts where voltage and current are not proportional, that is, that don't follow Ohm's law, and these are called non-ohmic elements. Let me give two leading examples. The first is the diode. With a diode, even when you apply voltage, the current doesn't smoothly increase in proportion to it. It has a peculiar property where it suddenly starts flowing from a certain point. If you draw a graph of voltage and current, it's not a straight line but a bent one. The second is the filament of an incandescent light bulb. As current flows and the filament heats up, its difficulty to flow, that is, its resistance itself, grows. So for this too, voltage and current are not proportional. As you raise the voltage, the resistance increases, so the current does rise, but the rise gradually slows. As a graph, it becomes a curve whose slope gently flattens out. For parts like these, you can calculate V over I at one point, but that value isn't the same throughout. It changes with conditions, so you can't treat the resistance as a single fixed value and apply Ohm's law directly. On the professional scene, before starting a calculation, you first check, is this even a part where Ohm's law works? A resistor is okay. A part like a diode or a bulb calls for caution. That one pause is the eye of someone who knows their stuff. Now a quick check to confirm your understanding. Again, 3 questions you'll trip on if you don't really get it. Give them a little thought. Question 1. You connect a 4 ohm resistor to a 12 volt source. How many amperes flow? Number 1, 3 amperes. Number 2, 48 amperes. Number 3, 0.33 amperes. Question 2. Without changing the voltage across a resistor, you double only the resistance value. What happens to the current? Number 1, it doubles. Number 2, it stays the same. Number 3, it halves. Question 3. Ohm's law V equals IR applies cleanly only to parts where the resistance is constant. Is this true or false? Have you settled on each answer? Let's check them on the next page. Alright, let's check the answers. The answer to question 1 is number 1, 3 amperes. Current is voltage over resistance, 12 volts over 4 ohms, which is 3 amperes. Just use I equals V over R directly and you're good. The answer to question 2 is number 3. It halves. For the same voltage, resistance and current are inversely proportional. Double the resistance and the current that flows halves. If you sought to make the resistance larger and the current also increases, be careful not to mix up the direction here. The answer to question 3 is true. Ohm's law applies cleanly only for parts where the resistance is constant, such as a resistor. For parts like a bulb, where the resistance itself changes with conditions, it doesn't apply as is. First, check whether it's a part where Ohm's law works. That was the important thing. How many did you get? Go back and review the ones you missed. So this time we've explained Ohm's law. First, voltage and current, which we'd learned separately, are actually in a proportional relationship, and the proportionality constant was the resistance. Putting that into a single equation gave V equals IR, voltage equals current times resistance. And since this equation can be reshaped to fit what you want to know, when you want the current, it's I equals V over R. And when you want the resistance, it's R equals V over I, each found with a single division. But there was also an important premise. This holds cleanly only for parts where the resistance R is constant. That's exactly why you can't apply it as is to non-ohmic elements like diodes and bulbs. The one pause of checking is this a part where it works before calculating is what pays off. Looking at it this way, today's story connects along a single thread. Voltage and current are proportional through resistance, so reshaping the equation lets you calculate both the current and the resistance, but only within parts where the resistance is constant. Keep in a corner of your mind the sense that you've now reached the entrance to handling circuits with numbers. That's all for this time. Thanks for watching.